Hello students, let's learn laminar flow in a narrow slit. In microscale environment, microfluids, narrow slits are used to create laminar flow, which is essential for precise control of fluid flow and mixing. It can be also used to enhance heat transfer between fluids by increasing surface area contact between the fluids. Example heat exchanger. In filtration, narrow slits are used to create laminar flow, which helps in separation of a particle based on their size. Example membrane separation process. In laser cutting, narrow slits are used to create a laminar flow of gas, which helps in removal of molten material from cutting area.
Now let's consider two vertical plates forming a narrow slit placed vertically in a way it's forming a narrow slit. So there is a space, a small gap in between these two plates. That gap is of twice B length. While this plate is having width W and length L. So fluid is flowing on this plate like this. This flow is laminar flow and fluid is Newtonian and it's flowing due to gravity. So whatever fluid is entering is coming out. Because of two plates, here pressure is forming at datum. Pressure is forming. So at datum Z equals to 0, P naught is the pressure and Z equals to L, PL is the pressure. This pressure is equals to pressure at length L plus rho GL into rho G naught. Because of density and gravity, pressure is acting on the fluid. So this pressure acting on fluid is equals to this. So total force acting on fluid is equals to length into width of the plate P naught minus PL per unit length, right? Whereas I say P naught is equals to this P naught plus small P naught plus rho G naught and PL is equals to PL plus rho GL. Now to find momentum flux, consider a shell in between this. This narrow slit is like this. This is of length L. with W. This narrow slit is having thickness twice B. Now consider a shell on it. On X plane. Here this is my X axis. This is my Z axis. Fluid is flowing like this on Z axis. Therefore velocity Vz only. And velocity on other direction is considered 0. That is Vy Vx is equals to 0. So this shell is of delta x, small width, very small width. So momentum flux in z direction. Momentum flux acting on z direction is because of fluid flowing in z direction only. Fluid is flowing like this, Vz. So velocity is only in z direction, unidirectional flow at surface x. So what is the molecular momentum flux distribution? What is the molecular momentum flux distribution? It's due to shear stress, right? So shear stress acting on fluid at distance x on the shell is tau xz, x on x surface, z on because of z direction at x surface, then leaving not leaving it's in negative direction, so minus tau xz at x plus delta x. So L into W, length and width of the width of the plate into tau xz at x minus tau xz at x plus delta x. Now assumptions of laminar flow in narrow slit. Consider a Newtonian fluid is flowing in narrow slit formed by two parallel walls at distance twice b, length L and width W, as shown in figure here. B is very less from W and W is very less from L, where W and L, these are length and width of the plate. Now steady state conditions. There are steady state conditions. Fluid is flowing in steady state. At z direction, Vz. So Vx and Vy is equals to 0. Unidirectional flow, incompressible fluid. Therefore, density and viscosity is constant. Laminar flow, Newtonian fluid. Let us consider a shell at x and thickness delta x. This no end effect, that is whatever fluid in is out at z equals to 0 and z equals to L. There is no disturbances, and thus the liquid at the edges are neglected. The fluid flow is under pressure and gravity. Where pressure is considered P naught for z equals to 0 and PL for z equals to L. Applying momentum balance at shell, we obtain rate of molecular momentum in across the surface x minus rate of molecular momentum out across the surface at x plus delta x plus external force acting on fluid. So LW tau xz x surface z direction at x minus LW tau xz tau xz x plus delta x plus external force LW P naught minus PL upon L into delta x at shell. Yeah. So delta x equals to 0. Now dividing by LW into delta x. Taking limit x tends to 0. We get tau xz x minus tau xz x plus delta x upon delta x plus P naught minus PL upon L equals to 0. So by calculus, formula of limit, we get function like this. Upon L. Now on integration, the tau x equals to P naught minus PL upon N dx So what we get here? Tau xz equals to P naught minus PL upon L into x plus C1. Now to find value of C1, we put boundary conditions. So what are boundary conditions here? So to find value of C1, putting boundary conditions. So at boundary conditions, tau xz is equals to 0 when x is equals to 0. Right? No shear stress between liquid and gas interface. So no shear condition. Liquid gas interface. I get C1 equals to 0. So C1 equals to 0, tau xz equals to P0 minus PL upon L into X. Now by Newton's law of viscosity, tau xz is equals to minus mu dvz upon dx. So putting this value on equation 2, dvz upon dx equals to P0 minus PL upon mu L into X. So on integration, dvz equals to P0 minus PL upon mu L x dx. What I get? Vz equals to P0 minus PL upon mu L x square upon 2, right, plus C2. Now to find value of C2, I'll put second boundary condition. So what is my second boundary condition? At x equals to b. Now at x equals to 0, I have tau xz equals to 0. Air liquid interface. At x equals to b, that is at distance this. At x equals to b, what I have? Velocity profile. Velocity profile, that is equals to 0. No relative velocity between solid liquid interface. This is my solid interface. This is my wall. So solid liquid interface causing no relative velocity. That is also no slip condition. So no slip condition. So at solid liquid interface, putting Vz value equals to 0. Here I have minus sign. So minus P0 minus PL upon mu L into B square upon 2 plus C2, giving me value of C2 equals to minus P0 minus PL upon L 2 mu L into B square. Now substituting this value on equation 3, substituting value of C2 on equation 3. So velocity profile Vz equals to P0 minus PL 2 mu L B square into 1 minus x square upon B square. So this is velocity profile. By putting value of C2. At at x equals to 0, we need to find maximum velocity. So at x equals to 0, what is the maximum velocity? So putting value of x equals to 0, we get Vz max Vz at x equals to 0 P naught minus PL 2 mu L into B square. So 1 minus 0, that gives me Vmax is equals to P naught minus PL upon 2 mu L into B square. Now average velocity. What is the average velocity? So average velocity is equals to volumetric flow rate upon area. So volumetric flow rate is integration of 0 to W, integration minus B to B, Vz dx upon dy, dx dy in dx into dy upon dx into dy area. Now integration of 0 to W, dy is W. So numerator and denominator, they get cancel out each other. And what's left here is this. So Vz, what's the value of Vz? P naught minus PL upon 2 mu L into B square. So this is constant, so outside the integration, and this becomes integration of 1 minus x square upon B square into dx. So integrating this term, what I get, four B upon 3. So putting this value 4b upon 3, two mu L into B square into 4b upon 3. So how if you want to solve this, so it becomes x minus x cube upon b square, taking limits minus b to b, this becomes b cube minus b upon minus so solving this, what you get, 2b upon 3 plus 2b upon 3, which gives me value 4/3. Now you solve the denominator, that is integration of dx minus b to b, which gives me value 2b. So what we get here, p naught minus pl upon 2 ul b square, which is also v max. So 2b get cancelled out by 2 here, which gives me value 2 into 3, that is 2 into 3 of v max. So average velocity is 2/3 of v max, maximum velocity. So mass flow rate is m dot average velocity into area into density. So this is integration of 0 to w to minus b to b rho vz dx into dy. Now taking first integration, we get rho into w, these are constants. Vz is p naught minus pl upon 2 mu l into b square 1 minus x upon b square. Right. Now this term is constant, so taking out, I have to integrate only this term, that is integration of minus b to b 1 minus x square upon b square into dx. Right. Now integrating that, we get x minus x cube upon 3b square, taking limit minus b to b. So solving this, what I get, b minus b cube upon 3b square minus minus b minus b cube upon 3b square. So this I get, this becomes, solving these terms, what I get, 4b upon 3, right? So rho w b square p square minus pl upon 2 mu l equals to 4b upon 3 into 4b upon 3, which becomes 2 by 3 rho b cube into w into p naught minus pl upon mu l. So this is my mass flow rate. Thank you.